dream that one day this nation will rise up and live out the true meaning of its creed.
I did not do it. I did not kill Joffrey, but I wish that I had.
Hi all. This project is about emotion transfer on spectrogram of speech. We have called it as the SpectroGAN. This problem is quite important because there are many AI assistants such as Siri, Alexa and Google Assistant which want to sound more human-like. So the team for this project is Shashank, Ashwin and myself Vineet. Here in this project we have implemented a CGAN to transfer various emotions in speech using its spectrograms. We have optimized our CGAN model by checking with multiple configurations on the number of resonant blocks in the generator model, as well as changing the size of the fast Fourier transform length of the audio clip. We have also tested the model effectiveness on various speakers and languages, and have some interesting results to show. From the literature survey, we have found out that CGAN produces optimal results for style transfer applications. Traditionally, this problem has been solved using a multi-layer perceptron and by using signal processing features such as pitch, energy, zero crossing, and Mel frequency substance coefficients to transfer emotions in speech. Finally, modern deep learning methods have shown promising outcomes. So here in this project, we have used a novel approach to transfer emotions in speech by using a CGAN. For this project, we have used the RAVDES dataset, which consists of 24 professional actors, that is 12 male and 12 female, who have vocalized two lexically matched statements in a neutral North American accent. Each of these audio files are 3 seconds long, 16-bit, and have sampling rate of 48 kHz. For this project, we have downsampled the sampling rate to 16 kHz, and there are a total of 200 audio files per emotion. There are various emotions available in this dataset such as anger, calm, disgust, fearful, happy, neutral, sad, and surprised. For those of you that don't know what a CGAN is, here is a brief overview of it. Consider the model of the CGAN as shown in the slide. This has two domains, domain X and domain Y. If we pass a domain X image through generator XY, we get an output similar to domain Y. This is passed as input through GYX, which acts as the first cycle of the CGAN, also called as the forward cycle. Similarly, if we pass a domain Y image through GYX, we get an output which is similar to domain X. This is passed as input back through GXY, forming the second cycle called as the backward cycle. Finally, these generated images are passed through two separate discriminator models, DX and DY, to classify these images as either real or fake. One good feature about the CGAN is that it does not require a dataset of paired images.
The generator model for our CGAN is an encoder-decoder model. As you can see from the figure, the first few layers downsample the input image, and then there are 6 resonant blocks followed by upsampling convolutional blocks. The discriminator model of the CGAN is a patch GAN. The output of the model is a 16x16 matrix in which each value corresponds to a receptive field of 70x70. In other words, the discriminator model maps the input image of 70x70 patches into real or fake. These predictions are then averaged to give the final output of the model. The composite model is the model which ties the two generators and the discriminator. The composite model trains each generator separately and updates its weights. The weights are then shared with its discriminator and also the other generator. An update to each generator consists of minimizing 4 losses. First one is the adversarial loss, which is the loss between the generator and the discriminator. Identity loss is the loss, for example, when we pass an image from domain X into a generator X. Forward cycle loss and backward cycle loss are the losses associated with the forward cycle and backward cycle respectively. As a baseline experiment to check if our model is working, we first tried our model on facial images. As you can see from the figure, there is a transfer of emotion from sad to happy after 50 epochs. But this model is not perfect since we have not optimized our weights for facial images. Once we had a working model, we then moved to emotion transfer on spectrograms of speech. So what are spectrograms? Spectrograms are just visual representation of the audio signal as the frequency varies with time on the x-axis. So this is how we get spectrograms. We have first sampled the audio signal at 16,000 Hz and performed short-time Fourier transform with two different configurations. First is the FFT length of 512 and hop length of 256, and the second is the FFT length of 1024 and hop length of 128. After obtaining these spectrograms, we have padded zeros to get an image size of 260 x 260 pixels and 520 x 520 pixels respectively. The reverse conversion of spectrogram to speech is done using an iterative algorithm called Griffin-Lin algorithm, using the same FFT length which we had used to get the spectrograms.
In the interest of time, considering that all our results are audio files, we'll only show the best and the worst of our results. For a more comprehensive list of our results, please check the link shown on screen. Oh, and also headphones are recommended. We picked three emotion pairs which we found to be significantly distinguishable. Here are the results when we used a spectrogram of 260 x 260. For conversion from calm to fearful, the original calm input is,
Kids are talking by the door.
and the converted fearful audio file is. For conversion from calm to angry, the original calm audio file is.
Dogs are sitting by the door.
And the converted angry audio file is. For conversion from happy to sad, the original audio file is.
Dogs are sitting by the door.
And conversion to sad is.
Dogs are sitting by the door.
This is where our model did not perform well. We picked audio files not seen by the model, and the conversion and style transfer was poor. This is an audio file recorded from an unseen speaker. The original audio file is calm.
This project is fun.
The converted fearful audio is.
This project is fun.
And the converted angry audio is.
This project is fun.
One important observation here is that the model was able to generate speech from unseen script. Therefore, in conclusion, we showed that it works. We can embed emotion in speech through spectrograms, and for this task, generators with 6 ResNet blocks work well with spectrograms that were constructed using FFT length of 512. Also, we don't need an extensive lexically rich dataset for speech reconstruction. We just need a larger dataset with more expressions of emotion. These are our references. I would definitely pause the video and check them out. And finally, we'd like to thank Professor Keith Chugg and the TAs for a wonderful course and their constant guidance. Also, a shout out to AWS for providing us the compute resources needed for this project. And that's it from us. Stay safe, y'all.